Welcome to this tutorial on simple linear regression. What we will be learning in this tutorial is how to better understand the relationship of two or more variables using regression analysis. For example, let's say we want to study the relationship between advertising expenditures and sales. What might we expect? Well, usually the more we spend on advertising, the more sales we should have. So we would want to see if as advertising expenditures increase, do sales increase as well? And by how much? We might also want to study the number of hours we practice some task and the number of errors. In this case, we would expect that as we practice more, the number of errors we make should decrease. What we are interested in doing with regression analysis is to develop a model that helps us to understand if two variables are related and to help us to make certain predictions. For example, if we can develop a model to show the relationship between advertising expenditures and sales, we would be able to use that model to predict the sales for a given level of advertising. In regression, we define what is called a dependent variable, and that is the variable we are trying to predict. We will also define an independent variable, and this is the variable we will use to predict the dependent variable. We will use the letter y to represent our dependent variable, and the letter x to represent the independent variable. If we are trying to predict sales based on advertising expenditures, then y would be the sales. So our dependent variable is sales, that's what we're trying to predict, and advertising expenditures would be our independent variable x, because that's what we're using to predict sales. What about the relationship between practice time and number of errors? In this case, we are saying that as practice time increases, we would expect the number of errors to decrease. So we would try to predict the number of errors, and that would be our dependent variable y, based on practice time. So that would be our independent variable x. Let's talk a little more about what simple linear regression is. The term simple refers to the number of independent variables we are using in a simple regression. In simple regression, we have only one independent variable and one dependent variable, that is one x and one y, using that one y to predict x. The term linear refers to the type of model we are trying to create. In this case, we are trying to fit a straight line to the data to approximate the relationship between x and y. The term linear means fitting a straight line. So what we are doing in this tutorial is simple linear regression. Simple because we have only one independent variable, and linear because we are trying to explain the relationship between x and y using a straight line. We can also use more than one independent variable when we feel it will help with the fit of the model, and when we use more than one independent variable, it would be called multiple regression. So now that we understand what simple regression is, let's take a look at the model. And it looks like this. We have y is equal to beta naught plus beta 1 times x plus the Greek letter epsilon. This model is for the population. We will use another model with b's instead of betas when we discuss the estimated model using sampling, much like we used x bar instead of mu to approximate the population mean. Let's look at the components of this model a little more closely. Beta naught refers to the y-intercept of the line we are defining for this model. We will refer to this line as the regression line or the line of regression. So beta naught is the y-intercept, which means it is where the line would cross over the y-axis. That point would be beta naught. You can also think of it as the value of y when x is 0. At the y-axis, the value of x is 0, so when x is 0, whatever y is at that point would be the y-intercept, beta naught. Next, we have beta 1. This would represent the slope of the regression line. The slope tells us two things, whether the line is increasing or decreasing, and how steep it is. The last component of the model is epsilon, and that stands for the error that exists in our prediction model. As good as our model is, there is always a random error term that cannot be accounted for. Let's take a look at some examples of the regression line. Here we have an example that shows a line sloping upward. Because the line is sloping upward, it is showing a positive or increasing relationship between x and y. This means that as x increases, so does y, so the line slopes upward, and therefore beta 1, the slope, will be a positive number. The line itself is called the regression line, or the line of regression, and the y-intercept, beta naught, is here, where the regression line hits the y-axis. This next example shows a downward sloping line and depicts a negative linear relationship between x and y. When we have a negative relationship, we see that as x increases, y decreases, and that is why the line slopes downward. So beta 1, the slope, would be a negative number. The regression line is here, and the y-intercept is here, where the line hits the y-axis. Here is another example where we have a flat line across. This graph shows that as x increases, y remains the same, so there is no relationship between x and y. In this scenario, beta 1, the slope, would be equal to 0. So when there is no linear relationship between x and y, the slope is 0. The regression line is this flat line going across, and the y-intercept, beta naught, would be here where the regression line hits the y-axis. Beta naught and beta 1 are the population parameters for the y-intercept and the slope. Just like mu was used to refer to the population parameter for the mean, and the Greek letter sigma was used for the standard deviation, we use beta and beta naught for the population parameters of the y-intercept and the slope. We don't know the true population parameters unless we take a complete census, so when we get our data from a sample, we are getting what are called sample statistics rather than true population parameters. In regression, B0 and B1 are used to estimate the true population parameters of beta naught and beta 1. Just like we used X bar to estimate mu and S to estimate sigma, we use B0 and B1 to estimate beta naught and beta 1. So for a sample, the estimated simple linear regression equation looks like this. Now this y with something that looks like a hat on it is actually called y hat. And in the equation, y hat refers to the estimated or predicted value of y for a given x value. B0 is the y-intercept for the line, and B1 is the slope. So now we have all the components we need to define a straight line. We have the slope and we have the y-intercept. Now we are ready to look at some sample data so that we can calculate the estimated slope and the y-intercept. Let's start by looking at a graph called a scatter diagram. This graph shows us the relationship between x and y. We begin by drawing a horizontal axis and labeling it x, and a vertical axis and labeling it y. On the x-axis, we will plot our independent variable, and on the y-axis, we will plot our dependent variable. For our example, number of hours studied is the independent variable, and grade on exam will be our dependent variable. Let's take a look at some sample data that I have. Here I have two columns of numbers. One is with the number of hours students studied, and the second column has their corresponding grades on an exam. There are 10 sets of numbers here. To begin, let's draw our horizontal and vertical axes and label them by putting the number of hours studied on the x-axis, the horizontal axis, and grades on the y-axis, the vertical axis. Remember, we said that x is always the independent variable, and that's what we use to predict y, our dependent variable. In this example, we will be using number of hours studied to predict the grade. So x would be the independent variable, number of hours studied, and y would be the dependent variable, grade. Okay, so let's put some tick marks here, and let's put the numbers so that we can begin plotting the data. Let's begin with the first set of x and y coordinates. The first x is 2, and its corresponding y is a grade of 69. So plotting the coordinates of 2 and 69, we would put a dot for that observation somewhere around here. Now let's move on to the next set of x and y coordinates, and they are 9 and 98. So that would be around here. The third set of x and y coordinates is 5 and 82, and that would be around here. And if we do this for the remaining x's and y's, we get a scatter diagram that looks like this. If I had graph paper, it would be a little more accurate, but this is the best I can do by eyeballing it. We can see that the plot seems to be showing a positive relationship between x and y. That is, as x, the number of hours, increases, so does y, the grade. We can also see that a straight line would probably fit the data somewhere around here. So we can create a linear model to describe this relationship between x and y by finding the slope and the y-intercept that defines the line that fits this data the best. To find the line that fits this data the best, we will use our sample data to help define the line of regression, which is this line, the line that fits the data the best. That line will be the y hat line, where y hat is the predicted value of y for a given x. So for our example, it would be the predicted grade on an exam for a given x, number of hours studied. And b naught would be the y-intercept of the line, so it would be the value of y when x is 0. If x is 0, that would mean the number of hours studied is 0, and the y-intercept b naught would be the grade for 0 number of hours studied. b1 would be the slope of the line, and it tells us whether there is an increasing or decreasing relationship between x and y, and how steep the line is. For this example, we will expect to find a positive slope because it is a positive relationship between x and y. Another way to put it is that the slope tells us how much y increases for every 1 unit increase in x. So for every 1 unit increase in x, the slope tells us how much y would increase by. The last letter in the equation is x, and that is the number of hours studied. So we will multiply x times b1 and then add b naught to get y hat. Okay, so let's try to get that line using the least squares method. What we will do is find the line that fits the data the best. That line, the y hat regression line, fits the data the best when the distance of each of the data points is at its minimum distance from the line. In other words, you want to minimize the distance of each yi from each corresponding y hat. That is what is meant by the formula in the red box. MIN means to minimize, and then you can see that we are taking each yi, those are our observed grades, and we have 10 of those for this example. So we want to minimize each of those observed yi values from the line of regression. That would be the line that fits the data the best. You can see how I drew a straight line through the plotted coordinates. Those coordinates are from the sample data, and then I used my eyes to try to approximate where a line would run through those points so that it is minimizing the differences between each of those points to the line, both above it and below it. I eyeballed it here when I drew it, but we need to use a formula to find the exact line by finding two values, a slope and a y-intercept. Take a look at the formula in the red box again. yi represents the observed value of y for the ith observation, and y hat would be the predicted value of y for that same ith observation. So let's say, for example, we take an x value of 3. That is, the number of hours studied is 3. On the graph, we would look at 3 for the x value, and then look up to the line of regression and over to where that point is on the y-axis. And we would get a predicted y value, y hat, for that observation would be 69. Once we get an exact equation for the regression line, we will be able to predict that value more exactly, but it is approximately 69. Now, if you look back at the original sample data from a few slides back, you will see that there was an observation of x equal 3, that is 3 hours studied, and that observation had a corresponding observed y value of 71. So that dot yi represents the actual observed value of 71 from the sample data, and the y hat value represents the predicted value we would get from the line of regression. Our task is to define a straight line that minimizes the differences or deviations from each of those dots to the line, and that is what the formula in the red box is saying. Take each yi from each y hat and minimize that squared difference. Now that we understand what the best fitting line to the data would be, we need to calculate its slope and its y-intercept. Let's first start with the slope. Here you can see the formula, and we can define x subscript I as the value of x for observation I. In our example, we have 10 observations for x, the number of hours studied, so we would have x subscript 1, x subscript 2, x subscript 3, and so on until x subscript 10. So those are our x subscript i's. Likewise, y subscript I would be the value of y for the ith observation, and we would have 10 of those for each of the corresponding y sub i's. X bar would be the average of the x's, so we would add up all of the x's and divide by 10 in this case. And y bar is the average of the y's, so we would add up all the grades and divide by how many there are to get y bar. Once we plug in all of these numbers and calculate the slope, then we can calculate the y-intercept, b0, by using this formula. Notice that in this formula we have b1, the slope, so we need to first calculate the slope before we can calculate the y-intercept. So let's take a look at how we would do these calculations. Here is the sample data with the 10 observations of x and y, number of hours studied, and grade on exam. So we have two columns here, one for x subscript I, and one for all the y subscript i's. Now let's make some more columns with all the numbers we will need to calculate the slope. Let's start with the third column where we will have all the x sub i's minus x bars. And if you look back at the formula for the slope, that is the first component in the numerator of the slope. Take a look at the formula. Then we need a column for yi minus y bar, and that's the next component in the numerator for the slope. And then if you take a look at that numerator, you'll see that we multiply those, so the next column will be the product of the third and fourth columns, and that will help us to complete the calculations for the numerator. And finally, we need the last column, which is the third column squared, and that will give us the denominator of the slope formula. Before we fill in all of these columns with our calculations, we first need to get x bar and y bar. So let's add up all of the x's, and we get 48, and so x bar would be 48 divided by 10, and we get 4.8. Now let's add up all the y's, and we get 778, and then to get y bar, we divide 778 by 10, and we get 77.8. So now that we have x bar and y bar, we are ready to get all of the other numbers. Now we are ready to calculate all the numbers in the third column, and we get these numbers. Make sure you understand where all these numbers come from. The first number, for example, is negative 2.8. And how do we get that? We get that by subtracting the x value 2 from x bar, and x bar is 4.8. So 2 minus 4.8 gives us negative 2.8. Look at the column header, and you can see the column header says x sub I minus x bar. So that's what we just did. X sub I is x1, and that is a 2, and x bar is 4.8. For the next number, we get 4.2 by subtracting the next x sub I from x bar. So we get 9 minus 4.8, and that gives us 4.2, and so on down the whole column. For the next column, we get these numbers. Again, make sure you understand where all these numbers are coming from. The header of this column is yi minus y bar, so we take each yi and subtract from y bar. The first yi value is 69, minus y bar is 77.8. So we take 69 minus 77.8, and we get negative 8.8, and so on down for this whole column of numbers. Now that we have columns 3 and 4, we're ready to get column 5, and that will be each number in column 3 times each number in column 4. And here are the numbers we would get. Let's take a look at the first number. The first number is 24.64, and we get that by taking negative 2.8 times negative 8.8, and that gives us 24.64, and so on down the whole column. And finally, for the last column, we take the third column and square each value to get this column of numbers. So negative 2.8 squared gives us 7.84, and so on. And now we're almost ready to get the slope. We first need to get the sum of this column, and this is 320.6. If you look at the formula for the slope, the numerator is the sum of these numbers. You can see the capital sigma sign that tells us to sum. Our next step is to sum the last column, and we get 67.6. And this would give us the sum for the denominator of the slope formula. Here are those two very important columns and the slope formula. You can see that the numerator in the slope formula is this, so the sum of this column would go in the numerator. And the denominator of the slope formula is the sum of this column. Putting this all together, we get the slope equals 320.6, and we get that from here. And then we divide that by 67.6, which we get from the sum of this column. And now we divide and we get 4.74. So now we are ready to calculate the y-intercept B naught. We will need x bar and y bar to calculate B naught. Remember, we already calculated x bar as 4.8, and we found y bar was 77.8 on a previous slide. So now we have all the numbers we need to calculate B naught, the y-intercept. And we get B naught is equal to 77.8 plus 4.74 times 4.8. 77.8 is 77.8. 1, 2, 3. 77.8 is y bar, and 4.8 is x bar. And where did 4.74 come from? That comes from here, the slope. And we get a y-intercept of 55.048. So now we have our slope and our y-intercept, and now we can define our y-hat line. Substituting B naught and B1 in this line, we get our y-hat line. Y-hat is equal to 55.048 plus 4.74 times x. Now we can use this y-hat line, also known as our line of regression, to predict any y for a given x value. We would just plug in the x value and out comes y-hat, the predicted y value. Let's start on a fresh page here where we have our estimated regression line that we just calculated. Now what we're going to do is use this line of regression to predict y for a given x value. So suppose the number of hours studied is 3. That is our given x value. Remember when we eyeballed it, we said it was around 69. Let's see what it would be using this y-hat line. What would be the predicted grade on the exam? So what we're asking is, when x is 3, what is the predicted value of y? To answer this question, we use our line of regression, our y-hat line, and substitute in the number 3 for the letter x, as you see here. So we have y-hat is equal to 55.048 plus 4.74 times 3 instead of times x. And this would give us our y-hat, our predicted value of y for a given x. And that is 69.268. So if a student studies 3 hours, we would predict the grade to be 69.268. How good a prediction is this? Well, that depends on how good a fit the regression line is to the data. Anyone can draw a straight line through any data points and define it mathematically with a slope and a y-intercept. But that doesn't mean it's a good fitting model. Even if there is no relationship between x and y, we could still mathematically define a straight line that fits the data the best, but it would not be a good fit. So we need a measurement that tells us how well the regression line fits the data. One such measurement is called the coefficient of determination, and it tells us how good a fit the regression line is to our data. The formula for the coefficient of determination is shown here in the red box. R squared is the coefficient of determination, and to calculate it, we take something called SSR and divide it by SST, where SSR is defined as the sum of the squares due to regression. The way we calculate SSR is to take the sum of the squared deviations of each predicted value of y, that's each y hat, and subtract y bar, the average y. So it measures the difference between the predicted values and the average. The denominator is SST, and that is defined as the sum of the squares for the total deviation, and we find that value by taking the sum of the square differences of each yi, that's each actual observation, from y bar, the average. And finally, we have something called SSE, which is defined as the sum of the squares for the error, and that is calculated by taking the sum of the square differences of each yi from each y hat, each predicted value. It is important to know that SST is equal to the sum of SSR and SSE. So if we add SSR plus SSE, we would get SST. This will help us to make the calculation simpler, since if we know any two of these numbers, we can get the third number by either adding or subtracting, as you will see in a few moments. Let's go back to our original data. Here we have the data in two columns labeled X and Y. Now let's make a third column for the predicted values of y hat for all these given x's. So now we have to take each value of x, plug it in the regression line, and get this column of numbers. Make sure you understand where all these numbers are coming from. These are all the y hat values for each I observation. Take the first number, 64.528. How did we get that? Well, you take the x value 2 and plug it in the y hat line, so 55.048 plus 4.74 times 2, right? The 2 comes from the first x value, and if you plug that in the y hat line, you get 64.528. Then to get the next number, we plug in the next x value. The next x value is 9, so 55.048 plus 4.74 times 9 gives us 97.708, and so on until we have the entire column of predicted y values. So just to be clear, this column of numbers has the predicted values of y for each of the given x values. We have 10 x values, and so we have 10 y hat values. The next column will be for the error, and that is each yi minus each y hat, and we get this column of numbers. Take a look at the first number, 4.472. How did we get that? Well, we take yi, the first y is 69, and subtract it from the first y hat that we just calculated, 64.528. So 69 minus 64.528 gives us 4.472. Now the next column is the squared error, so it's the previous column squared, and we get all these numbers just by squaring the previous column. So 19.9988 is 4.472 squared. The next column measures the deviations of each y from y bar, the average. Remember, y bar was 77.8, so we take each y and subtract 77.8 to get this column of numbers. So for example, the first y value is 69 and y bar is 77.8. So 69 minus 77.8 is negative 8.8. And we do that for each of the 10 numbers in this column. And finally, the last column is the squared deviations. So it is the previous column squared. So negative 8.8 squared would be 77.44, and so on. Now to get SSE. In order to get SSE, we need to sum up the squared error column of these numbers, and we get 79.1215 for SSE. Next, we want to get SST. So we need to sum up the squared deviations column, and we get 1599.6 for SST. So let's review. We have SSE equal to 79.1215, and we have SST equal to 1599.6. Now, to get the coefficient of determination, we need to divide SSR by SST. But we didn't calculate SSR, we calculated SSE and SST. Remember that SST is equal to SSR plus SSE. So we get SSR by subtracting SST minus SSE. So SSR would be 1599.6 minus 79.1215, which is 1520.4785. Now we can go back to the formula for r squared and calculate it by dividing SSR by SST. And we get 1520.4785, that's SSR, divided by 1599.6 SST, and that gives us an r squared value of 0.9505. So our coefficient of determination is 0.9505. The coefficient of determination r squared measures the percent of variability in y that can be explained by the x variable. In this case, y is grades and x is the number of hours studied. So what we measured shows the percent of variability in grades that is explained by the number of hours studied. Since r squared is 0.9505, we can say that 95.05% of the variability in grades can be explained by the number of hours studied. One more measure of how well the line fits the data needs to be discussed, and that is the correlation coefficient. This measures the strength of association between x and y. The correlation coefficient is called r, and its values are from -1 to +1. A value of +1 means that there is a perfect positive linear relationship between x and y. So that means that all the data points from the sample lie exactly on the line of regression with no deviation, and that the line slopes upward. An r value of -1 means a perfect negative linear relationship between x and y. In this case, all the data points lie exactly on the line of regression, but the line is sloping downward. R can take on any value between and including -1 and to and including +1. If r is 0, then that means there is no relationship between x and y. To calculate r, we simply take the square root of the coefficient of determination and use the sign of the slope we calculated. The r here has a subscript of x and y, and it just tells us that r, the correlation coefficient, is for the values of x and y. Sometimes we just leave the x and y out and say r. So to calculate r, we take the sine of the slope, b1, and multiply the square root of r squared. So for our example, r squared was 0.9505. Now, if we just take the square root of that number, we don't know if r should be negative or positive, since squared numbers always lose their sign. So in order to know whether it is a positive or a negative number, we have to look at the slope. Is it positive or negative? And then we use the sign for our slope. In our example of grades and numbers of hours studied, the slope was a positive 4.74. So we use that positive sign, and we get r is equal to the positive square root of 0.9505, and that is 0.9749. Now remember, we said that a +1 would be perfect positive linear relationship, which is very rare. So positive 0.9749 would indicate a very strong positive linear relationship between x and y. So let's review what we've just done and try to understand the bigger picture. First, we calculated the regression line using the least squares method. We calculated the slope b1 and the y-intercept b0 and came up with this line to fit the grade data that we had. When we plot this y-hat line on a scatter diagram, we find it falls around here close to the data points. You can see how this line fits the data very nicely, and we saw that when we calculated r and r squared, this line is a very good fit to the data. Some of the data points are exactly on the line, some are above, and some are below. Let's take a look at the average grade y bar for this data. Remember, we calculated y bar by summing up all 10 grades from the data set and dividing by 10, and we got an average y bar of 77.8. So let's plot this line on the scatter diagram, and it would be around here. The average grade for the class y bar is 77.8. So now we have a line for y bar, and we have a line for y hat. Notice that the 10 data points are closer to the y hat line than the y bar line. When we calculated R squared, we measured how well the line fit the data by calculating SSR and SST. R squared is the proportion of SSR to SST. So what exactly is SSR and SST? Let's start with SST, which stands for the total sums of squares. SST measures how well the observations cluster around the y-bar line. You can see from the formula SST is yi minus y-bar squared, so it is taking every y observation and measuring its deviation from the mean y-bar. Let's say, for example, we have an observation point here, a student studying 7 hours with a grade of 100. So for this data point, x is 7 and y is 100. Now the difference between this grade of 100 and the class average of 77.8 is yi minus y bar, and this distance is here. This deviation is called the total deviation. That is what SST measures. Now the predicted grade y hat for 7 hours of study, x equals 7, is given by the line of regression, and that would be 88.228. Take a look at the formula for SSR. You can see from this equation that SSR, the sum of the squares due to regression, is the deviation of each predicted value of y hat, and the average y bar. So that would be the distance between the y hat line and the y bar line, or this distance. And this is called explained variation. SSR is the explained variation, which is the deviation between the predicted value of y and the average value of y. It is explained by the line of regression. In other words, the class average is a 77.8, so that's the expected grade without any additional information. But if we use number of hours studied to get a better prediction, then we get a y hat value of 88.228. So the difference between the class average and the predicted grade is what is explained by the line of regression, and that is why it's called explained variation. Explained by what? Explained by the number of hours studied, our x variable. But take a look at the graph. We have an observation point at 100. A student who studied 7 hours got 100 and not the predicted grade of 88.228. That deviation between the actual grade and the predicted grade is called error. SSE, the sum of the squares for the error, is shown by this formula. The difference between each yi observation and the y hat, or predicted value of y. You see we have yi minus y hat, and on the scatter diagram where would that be? Well, take a look at yi and the y hat line, and that is here, the deviation between the actual value of y and the predicted value of y, and that is called unexplained variation. It is the variation of y that is not explained by the line of regression, and that's what SSE is. So going back to our equation for R squared is SSR divided by SST, and you can see now that that means R squared is explained variation, SSR, divided by total variation, SST. So when we calculated our R squared value, we got 0.9505, and we said that that meant that 95% of the variability of grades can be explained by the number of hours studied. What that means here is that the line of regression, the y hat line, explains 95% of the variation in grades from the mean, but around 5% of the variation is unexplained by the line of regression, and that would be SSE. Now we are ready to test the significance of this relationship in a different way by looking at the slope of the line. Remember when we talked about the slope earlier, we said a slope of 0 means there is no relationship between x and y. The equation for a simple linear regression line is y is equal to beta naught plus beta 1 times x plus epsilon. The epsilon term we're not going to deal with because that is the random error. If the slope is 0, then y will be beta naught no matter what value x is, which means that the value of y does not depend on x, so there is no linear relationship between x and y when the slope beta 1 is 0. We use this understanding of the slope to conduct a hypothesis test to see if there is a linear relationship as follows. We would state our null hypothesis H naught that the slope is equal to 0, and the alternative HA to see if we find evidence that the slope is not equal to 0. If we find evidence to support the alternative hypothesis that the slope is not equal to 0, we can conclude that there is a linear relationship between x and y. Since we do not know the value of sigma for this distribution, we will be using a t-test, and the test statistic would be b1 over sb1, where sb1 is the standard error for the slope. To calculate the standard error for the slope, sb1, we use this formula. We need to first find s, the standard deviation for this distribution, and then divide it by the square root of the sum of the x sub i's minus x bar squared. And so s is the square root of SSE divided by n minus 2. From a previous calculation, we see that we found SSE to be 79.1215 here. Now to get S, we take the square root of SSE divided by n minus 2, and that is 79.1215 divided by 10 minus 2, which is 3.1449. So now we have S, we are ready to get SB1, the standard error for the slope. And that is the S that we just calculated over the square root of the sum of the x sub i's minus x bar squared. So SB1 is 3.114 divided by the square root of 67.6. If you remember back when we calculated the slope, we created a column of each x from the mean squared and added it up, and we got 67.6 over here. So this is the same number we're using again. Okay, back to our calculations. We get SB1 as 0.3825. Now we can finally calculate our test statistic, which is B1 over SB1. So it is the slope that we calculated earlier. Remember, it was 4.74. So we have 4.74 over 0.3825, and that gives us a test statistic of 12.3921. All right, let's look at what we have so far. We are testing to see if we have enough evidence to support the alternative hypothesis that the slope is not equal to 0. If we find this evidence, we will conclude that there is a linear relationship between x and y. We calculated our test statistic to be 12.3921. So now we're ready to use either the critical value approach or the p-value approach to solve this problem. Let's begin with the critical value approach, and let's use an alpha value of 0.01. Now, since this is a two-tailed test, we split alpha in half. So we look up alpha divided in half, 0.005. Since this is a t-test, we would look up our critical value in the t-table under n minus 2 degrees of freedom. Looking in the t-table under 8 degrees of freedom, right? N minus 2 is 10 minus 2, which is 8 degrees of freedom, and alpha divided in half, 0.005, we find a critical value of 3.355. So with a critical value of 3.355 and a test statistic of 12.3921, we can see, looking at the t-distribution, the critical value splits the distribution into rejection regions and non-rejection regions, and the test statistic falls around here in the rejection region. We are now ready to come to a statistical conclusion, and that, of course, would be to reject the null. There is evidence that the slope is not equal to 0, which means there is a significant relationship between grades and number of hours studied. We can also solve this problem using the p-value approach. To use the p-value approach, we must first calculate the test statistic, and we got 12.3921, so we need to look up that number in the t-table under n minus 2 or 8 degrees of freedom. Looking in the t-table, we find under 8 degrees of freedom, 12.3921 would be off the chart, and therefore the exact area under the curve for 12.39 can't be established from the table, but we can extrapolate the number to be less than 0.0005. Remember, for a two-tailed test, we double the value we got in the table, so 0.0005 times 2 is equal to 0.001. The rejection rule is to reject the null hypothesis if the p-value is less than or equal to alpha. Since our alpha value for this problem was set at 0.01, 0.001, our p-value, is less than 0.01, our alpha value, and therefore we reject the null hypothesis and find evidence that the slope is not equal to 0, which means that grades and number of hours studied have a linear relationship. That concludes this tutorial on simple linear regression. I hope you enjoyed this tutorial, and I hope you learned something.